All right. So in this section, we are going to be looking at deflection in beams using double integration method. Okay. But before that, one may ask, what is deflection? Deflection is simply the vertical displacement of a beam from its original position when subjected to load. Okay. Yeah, so you can see over here as we are having this diagram over here, you can see that this is a beam. Okay, this is a simply support beam. Okay, that is being supported at two ends or both ends with a hinge support. Okay, and you can see that it has a point load of P over here. Okay, so this point load, if it is more than uh, what the beam can carry, you realize that this beam is going to sag. Okay, so the sagging of the beam is what we are calling what? The vertical displacement, okay, of a beam due to what? Too much loading. Okay. So the vertical displacement of the beam uh, can be calculated for using the double integration method and also using the hot moment area method. But you realize that you have to know the hot um, double integration method before you can be taught the moment area method. Okay. In exams, if you are being asked to use the double integration method and you go and use the moment area method, you get everything wrong. Okay. It implies that you didn't follow the rules and regulations. So you have to know both method so that if the question asks or is being specific, you know the method you are supposed to apply. Okay. Good. So you can see over here in our first section, we have what? One, bending moment, and the bending moment is noted as what? Mx. Okay, good. And two, i- integrate for slope, and you can see the integral of the slope equation. Okay, yes, you can see the integral of the slope equation. And also in the third one, what can you see? You can see integrate again for deflection. Okay, yes, this may sound new to all of us, but when we dive in, we are going to actually know what it entails and how all of this came about. All right. Also, deflection in beams happen because the beam bends under transverse force, like point loads, distributed loads, or even moments could also even cause the deflection in the beam. Okay, good. In simple terms, it's how much the beam sags or bow when carrying the weight. So if the beam is not designed to be able to carry that weight, you realize that you are surely going to what? Meet uncertainties. Okay. That is effective what? Effective depth should go with effective thickness. Exactly. All right, let's proceed. So we are going to be looking at calculation of deflection in beams using the double integration method. And we are saying that deflection in beams using the double integration method refers to calculating how much a beam bends under load by solving the beam deflection equation for elastic curve through two successive integrations. Okay, good. I want to remember you that integration is the hot reverse of differentiation. Okay, if you are being given a relation such as, let me say, y is equal to 2x squared, and they say you should integrate it. Okay, take note that the y, the x, take note that the y, the x is equal to what? Y prime. Okay, or the first derivative. Okay, so I can write the differential of this to be finally equal to what? This is going to become 4x. Okay, good. Let's try to integrate this and see what we will also get. If we try to integrate this, if you are trying to integrate the y, you realize that uh, our equation is going to look in the form of what? If you try to integrate the y, then it implies that we have to what? In integration, what do we do? You add 1 to the exponent and use it to multiply the denominator. Okay, so that is going to look as 4x exponent 2 all over what? 2. At the end of the day, you realize that we are going to get our 2x squared again. Okay, so this is a proof that um integration is the reverse of what? Differentiation. Thank you. Understanding beam deflection. Please, if you have forgotten your concept of integration and differentiation, I'll urge all of us to try and visit it. Okay, that is why we were taught in building mass 1 and also building mass 2. All, everything you have been taught in the past, you will surely meet it in the future again. So you have to have your notes beside you. That is why I urge that good students should always have pen and paper beside them so that as the lecture teaches, they will be able to make or they will be able to jot down important points. At the end of the day, in the future, you realize that those points you have jotted down are actually your literature review. In other words, they are your reference material. Okay. All right. Let's look at understanding beam deflection. And beam deflection is the displacement of beam from its original position, just as I told you earlier, when subjected to load such as point load, distributed load, or even moment. Okay. Excessive deflection can affect structural integrity, serviceability, and aesthetics, even if stresses remain within safe limits. Let's look at the step to calculate deflection for slope using double integration method. Okay, yes, let's look at the steps for calculating the deflection and slope using the double integration method. Okay, all we have been trying to say from wherever we have started to where we have gotten to is that if you have a simply support as this beam you are seeing over here, okay, which is loaded at a point P. If the P is too much, or let's say the beam is not designed well, you realize that at the end of the day, what is going to happen? This beam is going to sag. Okay, so this beam is going to sag if the force is too much. Okay, so this displacement of the beam at the end of the day is known as the deflection, and that is what actually causes so many buildings to collapse. Okay, after this deflection takes place, you should know that the next possible thing that can take place is what? Shear force. Yes, shear force. This partial line I'm putting here was the initial position of the beam. Okay, now you see how all the sagging has caused. Okay, and the deflection we say that is denoted as what? Y. Okay, in some books may also denote it with different symbols, but I still continue to say that the laws of physics are the same for all observers in uniform motion relative to one another. So no matter how you apply them mathematically, as to whether you are right or not, your mathematical statement should be able to validate that. Okay, so let's continue. Let's look at our steps to calculate deflection and slope using double integration method. The double integration method is a classical analytical technique used to determine the slope and deflection of beams. Step one. Step one. We said that we have to do governing equations. Okay. And the fundamental relation is the second derivative of the flexural member, okay, is equal to the bending moment, okay, is equal to the bending moment, which is equal to the mx we are seeing over here. Okay, where E is equal to our modulus of elasticity of the material. I is equal to the moment of inertia of the beam across the section, and also y is our deflection function. If they are calling it a function because you can see that x has been put into brackets in it, the x you are seeing is, don't get scared, okay, is s is just the span of the beam, okay, and the y is the deflection. So we are just still talking about the x and y axis. The cardinal point I gave you, if you still remember it, you have to hold it very well. All right, all right, all right. So let's proceed. Let's proceed. And in our step 2, but even before you can use this equation, you have to what? Find the bending moment equation. Okay, you have to find the bending moment equation. So if you have this beam like this, the beam you are seeing over here, it means that you have to come and calculate the support reactions first from whatever we taught you last semester. And then after that, what are you going to do? After calculating the support reaction, you come and take a cut. Okay. After the cut, you are going to get your bending moment equation. And that bending moment equation is what you are going to what? Equate to what? Is what you are going to equate to what? Uh, the second derivative of the flexural member. Okay, good. So let's proceed. And if I say flexural member, you don't need to get scared, okay? Flexural members are actually components such as beams. Exactly. Let's look at step 2. Step 2 is we integrate once to obtain the slope equation. And the first integral of our bending moment equation is going to give us the slope equation. Okay. Yeah, so if you are being asked to calculate for the slope as the support, it means that your first integral of the bending moment equation should give you your what? Your slope equation. Here we are saying that our dy dx is the slope of the elastic curve. Dy dx is the slope of the elastic curve, and c1 is the constant of integration. Take note that c2 will always be 0 because c2 will always be 0 because the cut was taken at the hot right hand side. Okay, exactly, exactly. Also, in our step 3, we are going to do the second integration, and the second integration is what is going to give us our deflection equation, which is what? The y you are seeing over here. And you see that in this case, they just put the first integral in the hot, second integral. It's not anything too scary. They just came to put the whole of this, okay, in this formula. In this formula, you see, those who have been using the laptops, I know you should be very much familiar to this, okay. So that is the x plus c, okay. So they came to carry the whole of this and they came to put it in it. That is all they did. Okay. That is all they did. So the whole of this in the bracket is just what? Mx. Okay. Don't get confused. In the bracket is just mx. And in the step 4, but even before the step 4, where we are saying the value of our C2 is another constant of integration. But remember that always your C2 is going to be equal to what? 0. Okay, let's look at the step 4. In the step 4, we have to apply the boundary condition. And boundary condition depend on the type of support. Also, simply support beams has also for simply support beam, deflection is 0 at the support. Take note of this. Always for simply support beam, deflection is going to be what? 0. All right. Cantilever for and also for cantilever beams, deflection at also for cantilever beams, deflection and slope are 0 at fixed end. Fixed end. So the deflection will only occur at the hot pre end. Okay, if the thing is supported at this side, you realize that no matter what the deflection, it is this part that will bend at the end of the day. Okay. Yes. As to whether the load is a UD or a moment or point load, whatever. Okay. No matter what, you realize that it will be hard for this part to bend, but it is here that has a high possibility of bending. Good. So in our step five, in our step five, in our step five, we say that we solve for deflection. Okay. That is, we substitute the constant back into deflection equation to get the elastic curve of the beam. From this, slope and deflection at the point can be calculated for. And the main reason why we do the boundary condition in the step 4 is to what? Calculate for the constant C1 and C2 after the what? Integration. After, when you do the first integration, you're going to get C1. And then after the second integration, that is what is going to produce the C2. Okay. And to know the value of your C1 and C2 without knowing the values, you can't proceed. That is why we do the boundary conditions. Okay. Exactly. So let's take a look at this chart. And this is a double integration method, okay, which is being used to calculate for, let me say, a simply support beam loaded at midspan. Okay. So for the left of load, you see, this is the left of the load, and you can see that this is also the hot right of the load. Okay. So the calculations has been done for each and every one respectively. Okay. Exactly. So you see, as we discussed, just as we discussed, so you can see that this is our slope equation over here, and also what is our deflection equation? This is obviously going to be our deflection equation for the left hand side, and that is how this formula came about. That is how this formula came about. Okay. In moment area method 2, I'm going to teach you how this method came about. On our right hand side, you see what we're also having over here. Yes, on our right hand side too. I hope you can also see what we're having over here. Okay, let's quickly proceed, and at the end of the day, we'll still be coming back to this, and you may get to understand how all these formulas work in real life. Okay, good. So an example, and the example we want to look at is simply support beams with central point load. Okay, for a beam of length L with point load P at midspan, our maximum deflection is surely going to be at the center. And the formula to calculate for the maximum deflection is this. If you know this formula, it is good, because obviously in the examination hall, you can use this to calculate for it and write the answer somewhere. So if you use the double integration method and you didn't get that answer, you will know whether you are wrong or not. Okay, good. This result comes directly from applying the double integration method with appropriate boundary conditions. Take note of these key points, and that is double integration method, or in double integration method is, let me say, systematic. And the first thing we are supposed to do is what? We have to derive the bending moment equation. But even before we derive the bending moment equation, we have to calculate for our support reaction, which I hope each and every one of us know by now. Then later we can come and find our um later we can come and derive our bending moment equation. Then secondly, we come and do integration twice. Okay. Then we apply the boundary condition to calculate for the hot constants C1 and C2. I think that is all. Also, we are saying that um, the double integration provides an analytical solution for statically determinate beam. When do we say a beam is statically determinate? A beam is said to be statically determinate when the hot reactions are equal to 3. Okay, good. And also, double integration method provides, let me say, or is useful for academic study and practical design check in structural engineering. Okay, so it's very, very, very applicable in real life, and it is good to know it. Okay, exactly. Double integration method for beam deflection was developed from the work of 18th to 19th century mathematicians and what engineers, practically rooted in Leonhard Euler and Daniel Bernoulli's formulation of the Euler-Bernoulli beam theory. It was not discovered by a single person, but evolved as engineers applied calculus to structural mechanics. Okay. Its contribution lie in providing a systematic way to calculating beam deflection, which is essential for safe and efficient structural design. Let's look at the histories governing the double integration method. The Leonhard Ehlers in 1707 to 1783. That is his lifespan or his duration on Earth. And Daniel Bernoulli, that is 1700, or let me say to what? 1782. Laid the foundation of beam theory by relating bending moment to curvature of beams. Okay. Their work led to Euler-Bernoulli's beam equation, which is the starting point of double integration method. And that is this that you can see. Okay, always you have to take the second derivative of the flexural member. Okay, yes, and equate it to the bending moment equation. And then at the end of the day, you are going to do your, let me say, integration twice, apply your boundary conditions to find your constants. You realize that life is going to become much more easier. You realize that life is going to become much more easier. I will urge you that if you have any question to ask, you can type that in the comment section. I will review that in the course of the day, and I will surely give you a feedback. I will surely give you a feedback. All right, let's proceed. Later, engineers in 19th century formulated the double integration technique as a practical way to solve this equation for real-world structure. Contributions to engineering. That is the contribution that double integration method has brought to us. The double integration method has had profound impact on structural and mechanical engineering. One, analytical precision. Okay, and that is it provides exact solution for deflection and slope in statically determinate beam. It ensures engineer can predict how beams bend under load even before construction. Two, the safety and serviceability. That's it. It helps excessive deflection. These are all, let me say, the contributions. So, but the contributions have been grouped into safety, analytical precision, foundation of molding method, versatility, and let me say, yes, I think that is all. Okay. So we just want to look at a few of them and then we proceed to our calculation. We proceed to our calculation. So we say it in safety and serviceability, we say it ensures compliance with building codes that limits allowable deflection. Also, in a foundation of molding method, it has served as the base for more advanced technique like Macaulay's method, um, moment area method, and finite element analysis. Even though computers now handle complex structures, the double integration method remain a teaching cornerstone in engineering education. Okay, so the versatility is application to different load conditions: point load, distributed load, and applied moment. Also, it is used in civil mechanic, aerospace, and naval engineering for beam, shaft, and frames. What are our key takeaway, or at the end of the day, what have we learned? We have learned that double integration method is not for the invention of a single person, but the mathematical evolution of Euler and Bernoulli's beam theory. Okay, that is why I'm urging each and every one of us to be able to learn hard, so that at the end of the day, we can also propound a theory that can make life much more easier. If they hadn't discovered that, it means that buildings would have still been collapsing in today real life more, and we wouldn't know the solution of that. Okay, but because of them, when a building is designed by structural engineers, or let me say by an architect, if you know all these formulas, you can be able to what? Calculate for the what? Deflection, the shear force, the bending moment, some of all these things. You take the support at the what? You first of all you take all the beams and calculate for all the shear force and bending moment. Also, you come and calculate for the deflection to check whether the beam is static. You see, you have to analyze the structure very well. You also take the columns and you see you do all your load calculations. In our lecture 5 or 6, we are going to be doing column calculations, and you see how to apply some of all these methods. So it's very much important. Okay. If you don't know your analysis very well, someone may deceive you, and at the end of the day, you may also be in trouble or may even be in prison. So you and I are obligated to know this very well, so that in future we can even also be able to teach someone for him or her to be able to understand. All right. It contribute to enorm- enormous. Okay, that is, it gave engineers a reliable analytical tools to predict deflection, ensuring structures are both safe and functional. Even today, if even today, it remains a fundamental method taught worldwide as the gateway to understanding structural behavior. So let's look at our example one. Let's look at our example one. Let's look at our example one. So our question says that calculate the rotation at the support. Show the maximum deflection is at midspan, and also calculate the maximum deflection of the beam below of the beam below. All right. So first of all, when we have a question like this, what is the first thing we are supposed to do? The first thing we are supposed to do is that we are supposed to repeat the question for 1 mark. Okay. We are supposed to repeat the question for 1 mark. So over here, I'm going to be writing my given. Okay. And in the given, first of all, I want to put the questions that they're asking us to find. They say we should calculate for the rotation at the support. So the rotation at the support is definitely going to be theta A, which we don't know, at the supports. Okay. So theta A, we don't know, comma, let me say theta B, we don't also, or C. Theta C2, we don't also know. So the rotation at C2, we don't also know because there are only two supports. So let's say that let's take that to be our I. And our I, what are they? telling us to calculate for again. We should also show that the maximum deflection it has made span. So we will use a diagram to denote that. And also calculate the maximum deflection of the beam below. So the maximum deflection in this case is going to be what? Y maximum. And that one too, we can say that we don't know. Okay, good. The question that was given to us over there, which is our original problem, is just a simply support beam. It's a simply support beam that is having two supports. That is having two support. That is a roller, a roller, and a hinge support. Anytime you see this, don't get confused. Okay, I told you this is the same as a roller. All right. And the point load on top of it was 80 kilonewton. 80 kilonewton. This point is our A, and this point is our B. B. We can also see that this point is our C. Finally, we can say that this is our original problem. Finally, we can say that this is our original problem. So if we are good to proceed, then it implies that we can proceed. Then it means we can now start from our solution or continue from our solution. And in our solution, we can now pull down our free body diagram and take moments at the supports and proceed. In our free body diagram, this is just the same as this. And if here is A, it implies that this is going to be our reaction at A, and this is also going to be our horizontal force at A. Also, this is our point load of 80 kilonewton. This is our point load of 80 kilonewton. And they said the span. We have here 4 meters. And we have also here to be 4 meters. Here is just going to be one support, one reaction. So this is our reaction C, since this point was B. So you can see that we have just drawn the free body diagram. Consider we have just drawn the free body diagram. Okay. Let me quickly denote over here free body diagram and let's accelerate. So this is our free body diagram. Okay. So now it means that we have to take um we have to find for our reaction before we can proceed. Okay, without a reaction, you can't proceed. I know that there are so many shortcuts, but if you use shortcuts, you will lose the marks. Okay, the marks, even how to get the marks is a problem, and now you are coming to lose some again. So you have to adopt all the method I'm putting behind or across for you so that life can be much more easier. If you fail to adhere, you are going to be in trouble. You can see that the number keeps reducing each and every semester. Okay. And we all have to try a possible way so we don't fall a victim. Okay. So first of all, we are going to be taking moments at A. We're going to be taking moments at A. So taking moments at A. Taking moments at A. And in this case, this time we are going to be taking clockwise to be positive. We are no more going to take clockwise to be and we are no more going to take anti-clockwise to be positive again. Okay. Anyhow you apply them, it still works. Whether you want to take anti-clockwise to be positive or whether you want to take clockwise to be positive, it will anyone work. Okay. Yes. Because the lecture says we should use clockwise to be positive. If you go and use anti-clockwise to be positive, you will face problem. That is the only advice I want to give you. Intelligence is being able to adapt to changes. When the drum or if the drum beat changes, you have to what? Adapt the dance. Yes, so you don't have to get scared. So in this case, I'm taking clockwise to be positive. Okay. And that is the sum of all what? The sum of all moments about A. Sum of all moments at A is equal to 0. So we could quickly take the moments and proceed. So that implies that we said that moment is equal to force times perpendicular distance. Okay. So if we put our compass over here and you open to 80 kilonewton and you rotate, you realize that the 80 is going to what? Multiply the 4, right? Good. So the 80 is going to take a clockwise moment, so it's going to be positive. So we are going to say that we are going to multiply 80 kilonewton times 4. 80 kilonewton. So 80 times 4. 80 times 4. Okay, and the other one, we are still standing at A. If we open to C, if we follow the direction, realize that this time we are going to take a what? A clockwise moment. So it's going to be what? RC, negative RC. If this is going to take anti-clockwise, anti-clockwise is negative this time. So negative, and it's going to be what? RC times 8. At the end of the day, you can see that there is nobody else. Because we are taking moment over here, all other forces over here is 0. All other forces over here is 0. So we will not include them. Yes. So we equate everything to what? 0. Let's quickly simplify. Let's all punch. 80 times 4. What are you getting? I'm getting 320 minus 8 RC is equal to 0. Okay, so when you group like terms, you realize that you're going to get 320 is equal to 8 RC. Okay, finally, what does it imply? It implies that we can say that our RC Or our reaction at C is equal to what? 320 divided by 8. And 320 divided by 8, what are we going to get? 320 divided by 8. We are going to get 40 kilo Newton. We are going to get 40 kilo Newton. Please, you have to try and adopt this method so that you don't lose all the mark. That is what I will beg you to do. Okay, exactly. Now we also have to come and take moment at the last end, C. So taking moment at C. So taking moment at C. And now taking moment at C, we have to put down our rule. The rule is we are saying this time we are taking clockwise to be positive. Okay. And that is the sum of all moments at C is equal to 0. Let's quickly go and take our moment and see how life can be much more easier. Now, let's say we are standing over here. We are standing at C and we'll be taking a moment. So if you follow this direction and you take this moment, you realize that you are going to be moving in a direction of what? We're going to move in anti-clockwise. Okay. Since you are going to be anti-clockwise, it implies that it is definitely going to be, it is definitely going to be, let me say, negative. Okay. It is definitely going to be negative. So, negative 80 times 4. Okay, now let's go and take the other one too. We are still standing at C. If you are standing at C and you open to the last end, you realize that if you take the moment, your RA is going to move clockwise. So now it's going to be RA times 4. Positive RA times 4. Positive RA times 4. I already taught you that. That's why I don't want to waste much time on that. Okay. Yes. Times 8. Positive RA times 8 times 8. In this case, because we are taking moment at C, we can include the HA. Okay. So we can say that plus the HA is equal to 0 plus HA or the horizontal force at A. So times 0. Horizontal force at A times 0. Now we equate all of this towards 0. After simplification, minus 80 times 4 is going to give us minus 320 plus 8 RA plus 0 is equal to 0. After that, we group like them. When you group like them, you realize that you're going to get 8 RA is equal to 320. So you see what is happening over here. And this implies that for simply support beam that is loaded at mid-span, for simply support beam that is loaded at mid-span, always your reaction A is going to be equal to your reaction B. Okay. After the question we just saw over here, That is what I have discovered. Okay. So next time, I'm not going to come and go through all this long method again. I'm just going to write what I'm just going to use a short approach to get the answer. Okay. But in exams, you have to adopt this method to be able to get the answer. Yes, that is, I'm going to use formula, but you can't use formula. If you use formula, you will lose the mark. And you know the consequences of that. It could cause you to fail or go for a resit. So it means that you have to adopt to the traditional method of doing it. Okay. Yes. So this one, you are going to get 40 kilonewton. 40 kilonewton. Okay. So that is it. That is it. If you want to consider all horizontal forces, if you want to consider all horizontal forces too, all the conditions are still the same. So let's say considering all horizontal forces. So considering all horizontal forces. And in the consideration of all of our horizontal forces, what is happening? You realize that we are getting, we have to pull down the rule, and the rule is what? If you are moving in the west, or let me say east side, you are definitely going to be what? Positive. Okay. Yes. That is the sum of all forces moving in the x-axis. Always reported to zero. Exactly. That implies that our h times a, or our ha is equal to zero. Okay. Our ha is equal to zero, or our ha times zero is equal to zero. All right. Let's quickly do our check and then we proceed. Let's quickly do our check. And in the check, in the check, in the check, what can we see? You realize that we are having a formula as Ra minus 80 kilonewton plus hot RC. But even before that, we have to pull down our rule first. Without the rule, we may confuse the examiner. Okay. So in doing so, we are just only saying that it's all the rules are still the same. Okay. That is the sum of all forces moving in the earth. Whereas if it is moving towards the north, it's definitely going to be positive. At the end of the day, we have to equate all of this to zero. Okay. Okay. So in our check, just as we're having a question over here, reaction R and reaction C are moving up, so they're going to be positive. It's only the 80 that will be negative because you can see that it is coming down, it is moving towards the south. So this is RA minus 80 plus RC. And at the end of the day, by substitution, if you write 40, 40 minus 80 plus 40, At the end of the day, what are we getting? If we don't get zero, it means that whatever we did, there is a problem with it. We have to go over and recheck. So we should all be getting zero. Okay. Also had zero. So from here, you can now say that we are now going to begin the main work. Okay. So you can see from wherever we started to where we have gotten to. You could take a screenshot, quickly take a screenshot, and then we proceed. All right. All right. So after calculating for your reaction, it implies that we have to draw the beam again. Okay. We have to come and redraw the beam again and represent all the reactions on it nicely for the examiner to see. Nicely for the examiner to see. Nicely for the examiner to see. So our load at midspan, which we know was 80 kilonewton. So this is 80 kilonewton. We know that this is 40. And this is also 40 kilonewton. This is our point A, B, and C. So we discovered that here was 4 meters and this part was also 4 meters. Okay, exactly. Exactly. All right. All right. So now we can establish our bending moment equation. So we are now coming to establish our bending moment equation. So see me writing over here. We are now coming to establish our bending moment equation. So I'm going to write bending, the bending moment the bending moment equation. The bending moment equation. Okay. So how do I get the bending moment equation? Before I can get the bending moment equation, I have to take a cut. Okay. I have to take a cut. Okay. So in drawing the bending moment equation, I have to redraw the diagram and take a cut. So I choose to take the cut at this part. Yes, I choose to take the cut at that part. So that implies that my cut is somewhere here like this. So in this case, this is going to be hot. Macaulay. So let's say MX. Okay, okay. And then we can now say that our reaction over here was 40 kilonewton. 40 kilonewton. 40 kilonewton. Okay. Yes, I took the cut somewhere here. So let's say my load is still here as 80 kilonewton. It hasn't been affected or touched. So this is my A. You can see that this is the B. Okay. Yes. So if I want to do my calibration, if I want to do the calibration, how am I going to calibrate my distance? My distance. Okay. All right. I want to hint on some vital point for you because we have two hot sections over here, or there are two segments, or the beam can be divided into two equal halves, or it is being loaded at midspan. You realize that we are going to have hot two lines. Okay. Yes, we are going to calibrate um uh our beam after taking the cut at two hot segments. So the first one is just going to be x, okay, and the second one is going to be x minus 4. So this is x. And now initially, you know that this is 4 meters, right? If this is 4 meters, to get a 4 meters, what do you have to do? You have to subtract what? X, or you subtract the 4 from the what? X. Initially, you knew that what was the value of the x? It was 8. So if you want to go back to the initial state, you go back to your 8 minus 4 and you still get your 4. Okay, so the laws of physics are the same for all observers in uniform motion relative to one another, as we can all see. So after this, we can now calculate for our BM value. Okay, we can now calculate for our BM value. So let me write BM values. This is my BM values. Bending moment values. So this is why I'm going to get my bending moment equation. This is why I'm going to get my bending moment equation. Okay, this one I'm going to get my bending moment equation. So watch out. That implies that the rule we are adopting is what? We say we are taking all clockwise to be positive this time. So we are taking clockwise to be positive. That is the sum of all moments at the origin should always be equated to or equal to what? 0. Yes. And then from here, we can now start taking our moments. We can now start taking our moments. So if you stand at A, let's even take the first one. The first one, you can see that it is an anti-clockwise moment. Okay. So negative what? Mx. Okay. Good. Now, if we are still standing at the origin here, you realize that the 80 is going to multiply the what? X minus 4. But the 80 is also going to be anti-clockwise, so it's going to be negative. So minus 80 times, let's say, x minus 4. I close the bracket. And also the other one is going to become, if I stand over here and I open to here, you realize that a distance of x is covered. Now I don't know it. So it becomes 40 times x. But this one is going to move in clockwise. So this time is going to be what? Plus 40 times x. Good, good, good. So at the end of the day, we can now equate the whole of this to 0. At the end of the day, we can now equate the whole of this to 0. Okay. So let's group like them and let's um mx stand alone. Okay, let's quickly group like them and let mx stand alone. So what do we have to do? We have to let everyone maintain over here and shift mx alone just to the other side. Okay, so this implies that we are finally going to be left with minus 80 minus 80 multiplying, dot means multiplication, x minus 4. Okay, brackets close, plus 40x. Now I can bring my equal to sign. I can move my mx. Okay, because we want it to stand alone. Minus. Now it's going to be positive. Okay, minus the mx. Exactly. Exactly. So at this stage, we can still rewrite this over here. I told you the other day that if what if a is equal to what b, then it implies that what b is also equal to what a. So if the whole of this relation is equal to just this, then it means that this can also be equal to the whole of this. Okay, yes, this can also be equal to the whole of this. This method we are using is the Macaulay's method. I think I have told you, and it means to find the equation that describe the deflection shape of beam from equations. Okay, using integration method. Exactly, using the integration method. Okay, so let's proceed. Let's proceed. So at the end of the day, we can say that our mx is equal to 40x minus 80. I didn't do anything. Okay, all conditions are still the same. Multiplying x minus 4. Okay, multiplying x minus 4. Okay, so whatever you are seeing at the top is the same as whatever you are seeing in the in our final step we are on now. Okay, on the final step on which we are on now. So, but for Macaulay's method, we are saying that what? But, but we are saying that what? Our mx is equal to what? The second derivative of the pleasure member. I hope you all agree with me. Yes. So if you are saying that, but this is equal to this, then it implies that we can rewrite this in the anywhere we see our mx, we can put this over there. Okay. Because I don't want to confuse you much, I'm still going to repeat the same thing again for you to see. Okay. But in our next examples, I'm going to be jumping a whole lot of steps because I assume everything has been watched. Don't forget to subscribe to my YouTube channel. Okay. Don't forget to subscribe to my YouTube channel so that you can always get notifications anytime I release any of the lecture videos. All right. So all what we are trying to say over there is that what this is the same as what EI, the second derivative of the pleasure member. And this we are seeing here is the same as everything you saw over there. 40x minus 80. Now we see x minus 4. X minus 4. Okay, so now since we already know that this is equal to this, we can rewrite our equation and then we name it as equation 1. Then from there we can even say that our steps has just what begun. Okay, so let's rewrite this to obtain our equation 1. Okay, so obtain equation 1. Finally, we can say that what our EI of the second derivative, okay, of the Fleischmann member is equal to 40x minus 80x minus 4. So in this state, we say that the whole of this is equation 1. So let me denote it as equation 1 for you to see. The whole of this is our now becomes our equation 1. Okay. So let's integrate equation 1 to get equation 2. Okay. So we say that let's integrate equation 1 to get equation 2. Let's integrate equation 1 to get equation 2. Just as whatever we learned initially, the rules were saying. If you were only jotting down important points, you would have had a reference material by now. Okay. So you could quickly reverse the video and go back and take some screenshot to compare. I'm sure if you are writing, you can still just flip from your note. Okay. So we say that let's integrate let's integrate equation 1 to get equation 2. So let's integrate equation 1 to get equation 2. And that implies that um the integral of whatever we had at the top over there that we are all seeing, the integral of this will be, I told you that integration is the what opposite of differentiation. Okay, yes. So this now becomes what this actually you are seeing over here is the same as EI into bracket what you see y prime. Don't get confused. Y prime. Okay. Uh-huh. So because we really need this deflection for something, so let me still maintain it. So this is d squared y all over the x squared. So the second derivative of this, eh, after the first integral, you realize that we are going to be left with what? Just dy dx. Okay. After the first differential, we are going to be left with dy dx. So dy dx, which is now going to be equal to what? In integration for the variable which is x. If you add 1 to the exponent and you get 2, you are going to now use that 2 to multiply the denominator. This x you are seeing over here It has an exponent of 1, but we don't write it. Okay, if you have eyes, you see. If you don't have eyes, you won't be able to see it. It's the same person is also have a coefficient of 1, but we don't write it. The same person is also having a subscript of 1. Okay, if you know, you know. So i- in your integration, you realize that is going to now cause the exponent of the x to be 2. So we are now going to get what? 40x squared. 40x squared all over what? 2. Take note that you can never use your 2 to what? Divide the 40. If you use the 2 to divide the 40, you'll be in problem. You'll be in a serious problem. So just leave it as it is because we are not done. Okay, we are trying to establish a relation that we can use to find for our constants. Okay, so anytime you integrate, you are going to surely meet a constant. So after this, we have to do for the other one too. The integral of this is going to look like 80 is the same thing, all divided by 2 times what? X minus 4, all into brackets, exponent of 2. This guy is also having 1. So at the end of the day, 1 plus 1 will give you 2. And you come and divide the whole of this by what? 2. You see what is happening over there. So as simple as ABC. As simple as ABC. So at the end of the day, because we have integrated, we are going to add what? Plus C over here. Okay. This C is not just any C, but it is actually the C1 we have been talking about. The constant C1 and C2. To calculate for the constant C1 and C2, it means that we have to apply the boundary condition. With time, we will get there and you see how we hot. You will see how that can also be established in real life to make life much more easier. So plus C1. Finally, you see that our equation 2 has been established. So this is now our equation 2. This is now our equation 2. This is now our equation 2. Also, let's integrate the equation 2 to get equation 3. Okay. Yes. So we said that equation 2 is a hot slope equation. Jot this down somewhere. Equation 2 is always your hot slope equation. And the equation 3 we are going to calculate for now is going to be your deflection equation. Okay. All right. You are surely going to make this in your exams. You can never skip it. Double integration method. Okay. You can never miss it. For your midsem, you can expect using moment area method. For that one, it's very simple. Okay, but for the exams, you are surely going to meet double integration method. Every year it comes. So I'll urge each and every one of us to take advantage of this and watch the lecture videos. Take time and watch the lecture videos. Okay. If you fail to plan, you're actually planning to fail. Thank you. So we say that let's integrate let's integrate equation 2 to get equation 3. So let's integrate equation 2, okay, to get equation 3. Let's integrate equation 2 to get equation 3. Let's integrate equation 2 to get equation 3. All right. So the integral of equation 2, how is it going to look like? If you integrate equation 2, now the differential of this is going to become what? The differential of this is going to become y. Okay. Let me say the integral of dy dx is just y. Okay. So the integral of dy dx is y. So we have to further continue. We have integrated this relation already. And we have to integrate the right hand side too. Whatever you do to the right hand side, you have to do the same thing to the left hand side. And vice versa. So the integral of this relation is going to look like what? In this case, to the x squared, we have to add 1 to it. If you add 1 to it, it's going to be 3. So the 3 are going to get, you have to come and multiply it to the denominator. Okay. So it's going to be what? 40x exponent 3. So 3 times 2 is what? 6. So that is why I'm writing 6. You can reverse the video and you just come back to whatever I said. Also, for this too, you realize that the integral, the integration is mainly tailored towards the what? X, according to the rules and principle. So this one too, you are going to add 1 to the exponent and you come and use it to multiply the denominator. So it's going to become 80 multiplying, let's say, x minus 4. X minus 4. Okay. Now bracket close. You realize that we are going to, this is going to be exponent of 3 all over 6. So in this case, plus what? You have to integrate the c1 too, and the integral of c1 is going to give us what? C1x. Okay. Plus c2 plus c2. Exactly. So this becomes our equation. This becomes our equation 3. We can finally say that this is now our equation 3. After the equation 3, we can now come to our boundary conditions. After the equation 3, we can now come back to our boundary condition. At this point, I continue to say that if you have any question to ask, quickly type it in the comment section. I'll come back and review that and give you a feedback. Yes, I'll come back and review that and I'll give you a feedback. All right. Let's look at boundary condition. So now we are coming to what? The boundary condition, and it only occurs at the supports. Okay. So this is our boundary conditions. The boundary conditions. So boundary conditions. Into brackets BC. Okay. Boundary condition into brackets BC. So I'm saying that it implies that what? At boundary condition 1. So let me say at boundary condition 1, at BC1, comma, the value of our x, okay, is equal to 0, and y is equal to what? 0. I know most of us are confused, but please don't get confused. The boundary condition, it occurs at the support. If you pick this beam, the boundary condition is over here. Initially at support A, what is the value of X? Is 0. And is there any deflection over there? No, there is no deflection. Okay. So you see, also if you come to boundary condition 2, boundary condition 2 is the other end of the beam. So this is boundary condition 1. This is your boundary condition 2, just at the support of the beam. Okay. So if you pick the boundary condition 2 over here, you realize that now your value of your X is what? 8. That is the whole span. It becomes 8. And the Y is still what? 0. So always for the boundary condition, always your Y will be 0. As a support, always your Y will be 0. For the X, the span will tell depending on where you are standing. Okay. Exactly. Exactly. So let me quickly move to wherever we were, and then we proceed. And this also implies that at boundary condition 2, at boundary condition 2, comma, our X is equal to 8 meters and our Y, same Y, is equal to 0. Okay. So now what are we going to do? We say that let's put our boundary condition 1 into equation 3 to calculate for the constant. Okay. Or better still, let's put our boundary condition 1 and boundary condition 2 into equation uh, 3. Okay, to calculate for the constant. Okay. So let's do that. Let's do that quickly. Let's do that quickly. So in this stage, we say that let's put, let me use a different color pen to write this. Let's put boundary condition 1, okay, and boundary condition 2 into equation 3 to get the constant. To get the constants. And what are the constants? The constants are C1 and C2. So to get the constant, what? C1 and C2. To get a constant C1 and C2. Okay, so let's quickly do that and let's see what we are going to get. Okay, good. Our equation 3. What did we get for our equation 3? This is our equation 3. Okay, so let's quickly write the equation 3, and then we can now come and put the boundary condition into it. So we said that our equation 3 is equal to EI into brackets, we saw Y, which is equal to 40x cube. 40x cube all over 6. All over 6 minus 80 all over 6 multiplying x minus 4 all cube, okay, plus c1 x plus c2. Okay. For those who are forwarding the videos, you may face challenges because I'm as I'm teaching alongside, I'm making references to some important points. If you don't take time to listen or play the full video, you realize that you're going to be missing a whole lot of things. Okay. So I'll urge each and every one of us to take time and enjoy the video. All right. So we said that this was our equation 3. If this is our equation 3, now we can put the boundary conditions into it. Okay. So now I'm going to say that at BC1, at our boundary condition 1, at our boundary condition 1, we realize that x was what? 0 and y was 0. So at boundary condition 1, x is equal to 0, comma, y is equal to 0. Let's substitute that into our equation and see the answer we'll be getting. So that is, we are going to get EI. Okay. And in place of the y, we are going to put 0 over there, which is equal to 40 all over 6. And now in place of this x, we are going to put 0 over there. Exponent 3 minus 80 over 6. Now you can see me writing 0 minus 4. I'll be telling you a secret just now. All cube plus C1 now 0 plus C2. You see what is happening over here? And the secret I want to tell you that you remember I told you that C2 is always going to be 0, and this is the reason why. Okay, but you have to solve for it. You have to prove it so that you don't lose the mark. In Macaulay's method, we don't accept negative answers. Okay, so anytime you spot a negative relation, you have to cancel it out. Okay, and I'm just going to cancel someone out of the equation now, even before I proceed, because that person has introduced a negative into the equation and we don't like that. Okay, that is one major rule of Macaulay. 0 minus 4, what is that going to give you? It's going to give you a negative figure. Okay, and due to that, we don't like it. Okay, so I'm going to cancel out. 0 minus 4 is going to give you negative 4. Okay, so we don't like that. So I'm going to cancel this. If it was maybe, let's say, uh, uh, 5 minus 4, we will accept it. Okay, or even if it was 4 minus 4, we will consider and write 0. Okay, but in this case, if it is 3 minus 4, we will cancel out. 2 minus 4, we cancel out. It continues like that. Okay, exactly. So from here, we want to quickly continue. So here is still going to, here, any number times 0 is still 0. Okay. So this is 0 is equal to 0 minus 0 plus C1 times 0 is still what? 0 plus what? C2. So we can now say that what? Therefore, C2 is equal to what? 0. Okay. We have to come and do for at boundary condition 2, 2. We also have to come and do for at boundary condition 2, 2. So let's do it over here. At boundary condition 2, at boundary condition 2, we are saying that x is equal to 8. X is equal to 8. And y is still equal to 0. Okay. Because at support B, there was no what? Deflection at the support. Okay. Yes, deflection normally occurs where there is no support. That is where it usually occurs. So in this one, we are going to be putting all of this into the equation 3. As simple as that. Okay. So first of all, what do you do? First of all, you have to repeat your equation 3 so that you don't lose the mark. So EI, you bring your y is equal to 40x cube all over 6 minus 80 multiplying x minus 4 minus 80 multiplying x minus 4 all divided by 6. This is cube plus C1x plus, let's say, C2. I hope my relation is correct as uh, we all wrote or had initially. Okay, so this is still our equation 3 because we say we are putting everything into the equation 3. I don't want to confuse you much. If not, I will just substitute it and move on. So you saw that even at our boundary condition 2, that was at support C, still the y was what? 0. So I'll put 0 over here, which is equal to 40. Now in place of the x, I'm going to be putting 8 over there. So 8 cube all over 6 minus 80 all over 6. Now this also become 8 minus 4 all cube plus C1 multiplying 8 plus C2 plus C2. Okay, okay. So let's quickly look through. If anyone must be cancelled out, we cancel him or her out before we even proceed. Since there is nobody, if you multiply the whole of this, you're going to get 0. And the whole of this, let's all do that together. 40 over 6 times 8, all into brackets, exponent 3, is going to give us this value. minus, let's quickly punch the other one too. Let's quickly punch the other one too. Minus 80 over 6. Bracket open, 8 minus 4. Or exponent 3 to, what are we going to get? You are going to get 2560 all over 3 plus, let's say, 8C1, okay, plus 0. Plus 0 because C2 is equal to what? 0. So this is how I'm going to denote that. Okay, yes. So we are saying that but C2 is equal to what? 0. That means that anywhere we C2, we are going to put what? 0 over there. Exactly. But we just calculated and we know now that C2 is equal to 0 in this relation. Okay. Okay. So what are we supposed to do next from here? The rest is no more physics. The rest become mathematics. The rest become mathematics. So let's quickly simplify. Let's quickly simplify this together and then we see how best we can be able to wrap up for the day. So the whole of this relation, if you punch the whole of this relation, you should be getting 2560. That is if you punch the whole of that relation into the calculator, you should be getting 2560. Okay, exactly. Plus your 8 C1. But take note that this value is going to be negative. Okay, because you have to move it to the other side. Okay, so if you move it to the other side, I'm now going to get minus 2560 is equal to 8C1. Now you want your C1. So it implies that you have to divide this. And this is going to give us minus 2560 all over 8 is equal to our C1. Okay, so you see, therefore we can say that our C1 is equal to, therefore we can say that our C1 is equal to minus 320. Minus 320. Because if you divide 2560 by 8, you're going to get 320. After getting that, we have to come and put our C1 and C2 into what? Um, equation 2 and 3 to get equation 4 and 5 correspondingly. Correspondingly. Okay. So after getting this, we said that what? I'm coming to draw a curtain. So I said that let's put the constant. Let's put the constants. So let's put the constants. into brackets C1 and C2 into equation 2 and equation 3 to get equation 4 and equation 5 respectively. So we said let's put the constant C1 and C2 into equation 2 and equation 3 to get equation 4 and 5 respectively. Okay. And that implies that you are going to put your C1 into equation 2, okay, to get equation 4. And you're going to put your C2 into equation 3 to get equation 5. As simple as that. So for C1, or what does that imply? Let me first of all, let me write my equation 2. What is the how did our equation 2 look like from the beginning? You see how our equation 2 look like. And equation 2 we said is the slope equation. So EI dy dx is equal to 40 x squared over 2 minus 80 over 2, and all conditions are still the same. Okay, so I'm sure I can be able to remember this and still write. So that is um initially this is the relation we had. We had our EI, which was dy dx, to be equal to 40 x squared all over 2, okay, minus 80 all over 2. Now we're having x minus 4 all over 2 plus our hot C1 because it was the first integral. So this is our equation 2. So you see I'm going to turn the equation 2 into equation 4 now, because we're already having equation 3. Okay. So I'm going to just put the constants into it, and that is all. There is nothing new over here. So it is still the same thing. I'm going to write EI dy dx is equal to 40x squared all over 2 minus 80 divided by 2. Okay, now bracket open, x minus 4 all squared plus the C1. And the C1, what did we get? We had negative 320. Okay, so in place of that, we are going to put minus 320 minus 320. So you see, this is now going to become our equation. This is now going to become our equation 5. And our equation 5 can finally be said to be our what? Slope equation. Okay. slope equation because the moment under the curve from first principle of differentiation is what? The change uh, in y over what? The change in the distance. Okay. Okay. So you are seeing it. You are seeing this we are having over here. And I'm saying that all what I'm trying to say is that the dy dx from Newton's first principle, so that dy dx is the derivative of the what? The function of f of x. Okay. Or this is the same as this. Okay. Which is equivalent to what? F of what? X plus h. Okay. Minus f of x all over what? H. And the h is the distance under the what? The curve. So in short, the dy dx is the slope. Okay. And what is the slope? You see that the slope is equal to what? Change in what? From land surveying, if you could remember, what is slope? Slope is equal to what? Rise over what? The run. In other words, how will you explain it? You see that slope is the change in what? Elevation. Okay. Slope is the change in uh, the vertical displacement over the what? Horizontal, uh, over the horizontal displacement. Okay. So if they say change in something, it means just the final one minus the initial one. Okay. So that is this. So it is due to this relation. Okay. Differentiation from Newton's first principle. That is why we are saying that what? Equation 2 and equation 5 is the what? Slope equation. Is the slope equation. If you integrate this, you are going to get a linear equation. If you integrate this, yes, if you integrate this, you are going to be left with a linear equation. So the integral of this equation again led to the linear equation, and the linear equation is now your what? Deflection equation. So let's find the deflection equation. Let's find for the deflection equation. So for the deflection equation, we said that what? They said for the deflection equation, which we all know, EI into bracket, we have y over here. This time I know that it is 6. So we had 40x cube all over 6 minus 80 into bracket x minus 4 all exponent 3 all over 6 plus c1x plus c2. And we know that this is our equation. This is going to become our equation. Let's say, or this was our equation 3. Okay. As we have been using for all this while. This was our equation 3. But we said that what? But we said that our C2 is 0. Okay. But C2 is 0. So let me put it over here. But C2 is 0. So, but C2 is equal to 0. I'm sure we all know that. We all know why C2 is equal to 0. Also, by substitution, we can proceed. Okay. So at boundary condition, no, we've already done that. It's the boundary condition that we use to calculate for the constant C1 and C2. Okay, so we already know the constant. And the C1, we had negative 320. So let's substitute that into it. So we are finally left with our EI to be, we are finally left with our AI to be equal to 40x cube all over 6 minus 80 over 6. Now I'm seeing x minus 4 cube minus 320. You have to remember to bring the s. There is s attached to it. If you don't bring the s, you fail. Plus 0 is equal to equation 5. Okay, this is going to give us our equation 5 since we already have equation 4. Okay, so this is going to give us our equation 5. Please, at this stage, if you have any question to ask, jot them down. When you meet me in person or groups, you suggest them out to me and we will discuss it together. Better so you can type them into the comment section and I'll rectify them for you or give you a feedback. Yes, good students should ask more questions, and more questions is what is going to validate your understanding or your research of whatever you have been learning. Okay. So from wherever we started to wherever we have gotten now, you see how it is. It is a gradual process. Okay. Without knowing one, you can't know the other. Okay, that is why we have been teaching you shear force and bending moment, all of those. It's for a reason. You see, today we are still using the moment calculation of reaction and all these things. So if you didn't know this from last semester, I think that this semester to you will still be struggling. No? And now we have come and add double integration to it. See. So please, I'll urge each and every one of us, the lecture video, let's take advantage of this to learn a lot and make the grades. Okay. If you are not, opportunity comes but one. If you are not able to make good use of this opportunity, it is either now or never. Okay. All right. All right. So at the end of the day, we are saying that our equation 4 is equal to what? This, let me say, so I think I quite make a mistake somewhere here. And then this equation that I wrote was our equation 2. And then the equation 2 is what is going to give us our equation 4. Okay. Yes. The equation 2 is what is going to give us our equation 4. And our equation 3 is what is going to give us our equation 5. Just as we were stating in our principle. Okay. Yes, exactly. Exactly. So at the end of the day, we see that our deflection equation. So let me outline them out. So at the end of the day, our deflection equation. At the end of the day, our deflection equation. Our deflection. To calculate for our deflection. To calculate for our deflection, or we have to use the formula equation what? Equation 5. Okay. And also to calculate for the slope, we have to use the formula of what? Equation 4. Okay. So these are the preambles I've given to you. Okay. Before we even proceed, let's quickly move back to our question and come back. Okay. Before we proceed, let's quickly move to our question and come back. And the question says, I remember the question says we should calculate for the deflection at midspan and also uh so the first question is saying that calculate the rotation at the support. Calculate the rotation at the support and maximum deflection at midspan. So what we are going to do is that for the rotation at the supports, I only calculate one for you because of the time. So I can choose to calculate for rotation at support A, and you calculate for rotation at support B and come and show it to me. Then at the end of the day, I'll calculate for the deflection. Better still, I'll be given an assignment. Try it out. It is a choice. Okay. Solve it and send it to me. I'll rectify that, and you see how best you can be also be able to test your brain even before the D day. Thank you. Back to wherever we were. Now I want to calculate for my I. Okay. Yes. So slope at support A. So I want to calculate for the slope at support A. So the slope at support A. Slope at support A. So the slope at support A. Let's quickly pick the formula and substitute it into it. Our slope, it means that we're going to be writing our equation 4. And equation 4 is equal to EI. EI, that is dy dx. I remember, dy dx is equal to 40x squared all over 2. Now we are having minus 80 to bracket open x minus 4 all squared all over 2. Okay. Since it was the first integral, it was just plus C1. Now we know that our C1 is equal to minus 320. So let's put it over there. Minus 320. So finally, what does this imply? At support A, x is equal to what? At support A, x is equal to what? 0. Okay, there is no movement. So let's substitute that into the equation and then we proceed. Okay, but I want to tell you that your dy dx, since I already told you that it is the same as the slope, I'm going to put it over here and we proceed. But what? Your dy dx is the same as the what? Your slope at A. Don't get confused. So in place of that, I'm going to just be writing theta A. Okay. So finally, you can see that our EI times the what? Theta A is equal to, by substitution, let's substitute the value of x into it. All over 2. Let's put this into it. This is going to be 0 all squared minus 80 over 2. This is also giving me 0 minus 4. Someone is going to definitely be cancelled out. All squared minus 320. So at the end of the day, this is going to still give me EI. Multiply my theta A. Okay. Yes. From whatever we learned so far, you realize that someone can easily cancel someone out because we said we don't want negative answers. So now I believe we can proceed. Now I believe we can proceed. 40 divided by 2, okay, multiplying 0 all squared, what are you going to get? You are still going to get the same 0 because any number times 0 is still 0. So the whole of here is going to give you 0, um, 0, okay. And then at the end of the day, 0 plus 0 minus what? 320 minus 320. And what does that imply? That implies that at the end of the day, we have to just do division to get our what? Our slope. So our EI, what was the value of our EI? I think the value of the EI that was given to us to use to solve the problem was 108. Okay, I forgot to give it to you. 108 times 10 exponent 3. Yes, 108 times 10 exponent 3. So this finally is going to give us to be minus 320. Now when you finally make theta the subject, since that is what we are looking for, you realize that our answer is going to be what? Minus 320 divided by the EI. Okay, good. But what? The value of our EI in this case is equal to 108 times 10 exponent, let's say 3 times 10 exponent 3. Okay, so let's quickly simplify by substitution. By substitution, if you do that, you are going to get your theta or your theta A or your angle at A to be minus 320 all over 108 times 10 exponent 3. So please let's quickly all point this together. Let's verify the answer. Minus 320 all over 108 times 10 exponent 3. And what are we going to get? What are we all going to get? We are going to get um minus 2, okay, 0.96, let's say 0.96, okay, 0.96, let's leave it this way, times 10 exponent negative 3 times 10 exponent negative 3. So this times 10 exponent negative 3 is the same as this. This is the same as this. Please don't get confused. Okay. If you run it, what I've written over there, the angle is measured in what? The angle is measured in rads. Okay. The angle is measured in rads. So this over here, don't get confused. And this is the same as what? 0.0. Better still, let me denote it all. This is the same as negative 0.002 point. No, the point will not come again. 296 rad. Okay. If you are not still much convinced and you still want to run, you can still finally go ahead to come and get your last or final answer to be what. Therefore, your angle at A to be equal to minus 0.00. If you run this, you're going to get 3 rads. Okay, 0.00 rads. Okay, 0.00 rads. That is for your rotation at what? A. So I believe you'll be able to do the other one on your own. I believe you'll be able to do the other one on your own. So let's also do the slope at support B if that is the case. Let's do the slope at support B. So the slope at support B. So the slope at support B. We already know the slope equation. We already know the slope equation. And we said the slope equation is equal to what we are having over here, right? And that was our equation 4. Okay, this was our equation 4 from whatever we just learned over here. Okay, so from our slope equation, let's quickly put the equation down and then let's see how it can be applied. So the equation was EI dy dx, okay, to be equal to 40x over 2 all squared minus 80 over 2. Now we are having x minus 4 all squared plus our C1. So you see, this still remains the same equation 4 because we're using it to calculate for just the slope. Equation 5 is used to calculate for deflection. We've not yet gotten there. So over here, we are saying that at support B, no, or slope at, it's supposed to be slope at support C rather, because that is where the support is. So the slope at support C, you realize that your x is equal to 8. So if you substitute this 8 into the equation, what are you going to get? You're going to get our EI dy dx to be equal to 40. Now let's put the 8 into the bracket, all squared, all over 2 minus 80 over 2. Now we write 8 minus 4 over here, all squared, minus 320. So let's quickly punch the whole of this into the calculator and see the answer you're going to get. Please take your time and punch it well. If you don't punch it well, you may not get the right thing that we are all going to be getting. Because of the time, that is why I'm trying to skip the systematic process. But I'm sure if you are still able to just punch all of this well, you should be getting the answers that we are all going to get. Okay, so it implies that at the end of the day, this will cancel this. Okay, so the EI, where we say this, but in this case too, we are saying that but what our dy dx is also equal to what? The slope at what? B. Okay, the slope at B, the slope at B. So that implies that we are finally going to get EI uh, of theta at B to just be equal to what? 320. Okay. So if the whole of this is equal to 320, it's as easy as that. It means that our angle at B is equal to just 320 divided by the EI. I believe we all know the value of the EI. So what is the value of the EI? 108 times 10 exponent 3. So 320 divided by 108 times 10 exponent 3 is the same thing, but in this case, in a different direction. Okay, it is showing that the beam is going to be displaced in a different direction. So this, so we had 0.00296, which is the same as what? 2.96 times 10 exponent negative 3. Okay, so therefore we can say that what our theta at B is equal to what? 0.3 rads. So for simply support beam, since we said that there is no deflection at the support, you should know that deflection is definitely going to be at the midspan of the beam, okay, because that is where the load is. Yes. So we want to calculate for the maximum deflection at midspan, and then we wrap up for the day. So this is the maximum deflection at midspan. So the maximum deflection at midspan. So first of all, we have to write the deflection equation. And the deflection equation is the one that has y in it. So our EI, now we have the y over here. Okay. And you see that this is equal to our 40 x cubed all over 6 minus 80 x minus 4 all cubed all over 6. Okay. Plus, or let me say minus 320 x. If you don't attach the x, you're in trouble. If you don't attach the x, you're in trouble. Plus 0. Now I want you to see it when the 0 is the C2. So this becomes our equation, or we know already that this is our equation 5. If this is equation 5, our deflection at midspan, x is equal to what? For deflection at midspan, we say that x is equal to, it's just 4. Okay, at midspan, the midspan dimension is 4. So if we are taking x to be 4, wherever we see x, we are going to put 4 over there in the relation. Okay, so this is going to be EI. You can see the y over here, which is equal to 40 all over 6. Let's put this over here 4 all exponent 3 minus 80 all over 6. Now this is 4 minus 4 cube minus 320 also multiplied by 4. At the end of the day, what are we going to get? We are going to get EIY, okay, to be equal to, let's quickly punch the whole of this and tell me the answer. 40 over 6 multiplying bracket open 4 exponent 3. I'm getting 1280 all over 3. Let's do for the other one. Minus 80 over 6. Okay. Now 4 minus 4 all exponent is definitely still going to be 0. You know that. Because any number times 0 is 0. Minus 320 times 4. You are going to get 1280. So when we further simplify this, 1280 over 3 minus, or let's say minus 0 minus what? 1280. What are we going to get? What are we going to be left with? So this implies that we are going to be left with our EI. To be equal to we're going to let the whole of this but before that, let me quickly review something before we proceed. Okay, let me quickly review something for my computation even before we proceed. Okay. Okay. So let me quickly review this for my computation before we proceed. Let's quickly punch all the whole relation into the calculator and see what we are going to get. Okay. Let's quickly all punch the whole thing into the calculator and see what we are going to get. So at the end of the day, I'm getting minus minus 2, 5, 6, 0 all over what? 3. And this is the same as what? Our EI y to be equal to what? If you change this to decimals, you are going to get, press SD, you are going to get minus 8, 5, 3.33. Okay, because we were using 3 decimal places for the other one. This one, so let's maintain 3 decimal places. So if I divide here by EI, if I divide here by EI. I believe now we are all grown. So let me just jump to the next step. Finally, we see that Y is going to stand alone. And our relation is going to become this minus 853.33 all over the EI. So this let's quickly simplify this and let's wrap up for the day. So our EI was 108 times 10 exponent 3 minus 853.33. So at the end of the day, if you punch the whole of that into the calculator, minus 853.33 all divided by 108 times your 10 exponent 3, you realize that you're going to get your deflection, which is Y, to be equal to negative 7.9, okay, 0, okay, 901. Let me maintain the three decimal place, but in this case, your answer is going to be in what? Your answer is going to be in meters, okay. But even before that, this, when you punch it, after the punching, we are getting all of this is times what? 10 exponent what? Minus 3 meters. Okay. Yes, because we are still workers and we say that we want all our calculations to be in what? Mm. To get this in it means that you have to multiply it by what? 1,000. Okay. So at the end of the day, after multiplying by 1,000, you are going to finally get what? So this is the same as 0.0, 0 point what? 0, 0, better still, let me denote this for the negative direction shows that the thing is moving down. Okay, so it is negative what? 0.007901. Okay, meters times what? 10 exponent 3, let me say um per meter. Okay, millimeters per meter. So at the end of the day, meter is going to cancel meter, and then you realize that millimeter will dominate. So finally, we can say that our answer is going to be Y is equal to what? If you multiply the whole of that, your answer times just 10 exponent 3. You're going to be left with minus, let me use a different color pen since that is one of the last answers I'm coming to right now. So now the answer is going to be Y is equal to minus 7.901. Okay, mm. That is if you want to leave an answer in hot. Since our question further went on to tell us that we should show or represent it, it means that after we have to come and redraw our hot free body diagram, and now we can represent all our information on it. Okay, then we can now say that we are done with the question completely. You can see how we just analyze the beam. Okay, you are expected to do same in the examination hall. Even you are supposed to even be able to do it far better than me. Okay, yes. For me, my time has passed. Okay, I'll be given more complex questions to solve and not these simple ones. So I wish you could score 100 over 100, A plus for me, so that at least I can be proud or I can be happy. Okay, yes. So the deflection, let me use a different color pen to denote that. This is the point load, and the point load was 80 kilonewton. 80 kilonewton. Okay, so I'm going to use a different color pen to denote that. So this is the deflection that the beam displaced. So at the end of the day, you see from here to here, from here to here is our y, which is equal to what? Minus 7.9. Okay, minus 7.9 mm. And at the end of the day, the angle that it is trying to move with, okay, you see this guy. Let me use a blue pen to denote it. Okay, this is the direction with which it may move in. Okay, and this is our support A. This was our support C. Okay, good. So this one too, you see that this one too will definitely move in this direction. After the deflection, you see that this guy is also going to move in this direction. Okay, yes, it will fall in that way. It will fall in that order. It will fall in that order. Okay, so finally, what are we saying? We are saying that our slope at A, we said that our slope at A was equal to what? Minus 0.003 rads. Okay, I hope you are seeing it. Yes, and also our slope at B was also hot. Or let's say our slope at C. Our slope at C. Our slope at C was also equal to what? Positive 0.003 rads. Okay, so this is a positive one. This is a positive sign. Okay, so since the deflection is negative, it shows a downward deflection. Okay, from the cardinal point I taught you last semester, if we could all remember. Okay, if you could all remember, said this part is positive, this part is negative, this part is positive, this part is negative. So because it is coming down, that is why it is negative. Assuming we didn't get a negative answer, it means that whatever we are doing, there is a problem with it. Okay, yes, but because we are getting a negative, it should tell you that we are more accurate. Okay, it should tell you that we are more accurate. So please, thank you very much for your time. Meet me in groups, in person, one-on-one, provided you have any question related to whatever we have learned today. Provided you have any question pertaining to whatever we have learned today. Good students should look for questions, look for past questions and solve past questions. Okay, if there is anything you don't understand, approach me or approach any lecturer so that at least you can start knowing some of the examination questions even before the time of the paper. If you want to wait before the time of the paper before you go and say that you are looking for some of all those things, it will affect you. Okay, it's because it will be assumed that you didn't plan well. That is why I'm saying that if you fail to plan, you're actually planning to fail. Okay,
If you fail to plan, you're actually planning to fail. All right, all right, all right. So on this note, my name still remain the same. Throw a dollar on my name if you find this video very, very, very much attractive and also very, very, very helpful. Thank you very much for your time. May God richly bless you all for your support also. Bye bye.